All right, everybody, let's get started. Good afternoon, everyone. Welcome to the North Carolina Museum of Natural Sciences. Hi, third floor. How you doing today? Good. Welcome to our lecture series, the Lunchtime Discovery Series, hosted here at the North Carolina Museum of Natural Sciences, and I am your host, Chris Smith. I work in education here at the museum, but my job is just to welcome you to the museum, welcome you into the Daily Planet Theater, and introduce you to our very special guest speakers that join us every single week here inside the globe and online to share their knowledge and insights with us so that we can learn more about what's happening in science, nature, conservation, education, and beyond. This lecture series, though, is coordinated and organized by the folks in the North Carolina Office of Environmental Education. Within the Department of Environmental Quality, they do the fantastic work of finding amazing people who are doing really cool work out there in these worlds, and then bringing them into the museum so that we can learn more about the stuff that they know a lot about. And of course, if you're watching the program here in the theater, thank you for joining us. After the presentation, we'll have plenty of time for your questions. So if anything comes up for you that you want to know more about, put a pin in it and we'll come back to it after the talk. And for those that are watching on the museum's YouTube channel, thanks for tuning in. You can also ask questions as they come up for you. Type them into the chat on YouTube. We're monitoring that so that we can feed your questions into the program live a little bit later in our presentation. But without further ado, let me bring up today's guest. Today we've got an expert in sustainability who is going to talk to us a little bit about this amazing thing called biomimicry. Everybody put your hands and welcome to the stage, Scott Pfister.
Thank you so much. While I get set up here a little bit, I know this presentation is going to be a little more advanced, and if there's any littles around, I have a question for you. What type of shoes do frogs wear? What type of shoes do frogs wear?
What type of shoes do frogs wear?
Yes.
Anybody got an answer? Wave at me. Flippers?
Flippers? Okay. Close. Open-toed shoes. Oh, I know. That'll sink in. Like on your car ride home, you'll be like, I got that one. All right, thank you so much for the opportunity and to be here back at the NRC. I'm super thrilled and honored to be a speaker. I've seen a lot of different speakers here. I've been in the chair online. I've seen some other speakers over at the Daily Planet. So it's really an honor for me to be here. And what a perfect venue for this subject. Biomimicry is so many, there's like little pieces of biomimicry all within this museum. So this is a really, really cool spot for this presentation as well. All right, so I just wanted to spend a few moments on my background. I was announced as a sustainability professional. I just wanted to make a note that I'm not really here on behalf of any previous employer or any organization, although some examples may come up through my career. So this really helps kind of shape why I got into biomimicry. I grew up with a backyard of a state park. So there was a fence line that separated my parents' yard from a state park. So I was always out on a creek or running around in the woods, just not getting into trouble, but always keep an ear open for mom yelling for dinner or come back to the house. So I went to Miami University in Ohio, and I was really interested. I loved maps, and I loved being outside. But I also liked cities, and I liked to know why did that road go there? Wow, that building's really cool. Or how does water get from the treatment plant all the way into this building? So I double majored in geography and urban planning. And I'm currently seeking a biomimicry specialist certification through a partnership between Biomimicry 3.8 and Arizona State University, which is all online. So there are professional certificates, graduate level professional certificates, as well as a master's degree through Arizona State University. I think there might be a couple other schools that have some classes or programs as well, just not coming off the top of my head. So thinking about my profession, so that's kind of how I grew up and where my mindset was at. I wanted to be outside, so I was a nature tour guide and then helped create a sustainability coordinator position for a golf resort near Charleston, South Carolina, which is really fun. I also worked here for DEQ, well, first Diener, then DEQ, 2 different tours of duty with the Environmental Stewardship Initiative program, which is a pollution prevention program focused on technical assistance, networking, and recognition. Wonderful program. And then I worked for Caterpillar. Most of you have probably heard of Caterpillar as well. And now Thomas Built Buses. So we make school buses. So I've been in the environmental world for quite some time. And just wanted to share this wonderful subject of biomimicry. And really this presentation, as you can tell, I double majored, so I changed my major like 4 or 5 times. So I didn't know what I wanted to do. I've changed jobs, you know, not super frequently, but a few times. And so this presentation of biomimicry is really, I think it's for the jack of all trades folks. It's for the students who don't really know what to major in, or those people in their career who don't really know what to do when they grow up. I'll be 44 this year, and I still don't know what I want to do. So biomimicry really holds a special place in my heart because of that, because it can be as narrow or as wide or as connected or independent as you want it to be. So let's do an exercise real quick. So everybody close your eyes, as long as you're in a safe spot. Folks on the 3rd floor, please be safe. So close your eyes, and I want you, while your eyes are closed, to think of a place where you find solace, where you can relax, where you want to be on weekends, on vacation. So think about that for a second. All right, so come back from your vacation, your mental vacation. And how many of you thought of a beach or a lake, or a few hands raised down here, or some water body, right? You're kayaking or fishing or something like that. How many people thought of trees or mountains or hiking, biking, walking? Yep, a few hands. How many of you thought of being in your friend's backyard or your family's backyard, having a cookout? There's a deep connection to nature. Mosquitoes aside and pollen aside, there's a deep connection to nature. I know springtime it's tough to be outside because of the pollen, and mosquitoes kind of pester us a little bit. But there is this deep connection with nature. And you know, we're a few years outside the COVID-19 pandemic, but there's so many studies that showed people wanting to get outside. National park numbers were just through the roof. State park numbers were through the roof, right? So that deep connection, just kind of hang on to that thought as we go through this slide. So what is biomimicry? I promised some folks in the crowd that I would define what biomimicry is. So just a simple definition is the conscious emulation of life's genius, or innovation inspired by nature. Those aren't my words. Those are Janine Benyus's words. And this is the first published in 1997. This is a seminal work that really helped spread the concept to the level it is today. And I mentioned earlier, there's universities that have programs in biomimicry. So this isn't just a book. It isn't just a concept. You can get a degree in this. And a lot of these global alumni are in many levels of different types of businesses, communities, injecting this methodology and tools into those businesses and communities. And in fact, Microsoft actually has a director of biomimicry. So that's a nice definition, but what's an example? How many of you have had clothing with Velcro on it? Everybody. Maybe some of you have Velcro on right now. Think about if you were to imagine the Velcro and under a microscope. One side has a bunch of hooks, and the other side has a bunch of loops. And the inventor of that was inspired after they were walking through some thicket or brambles, and they had those little seed pods. Probably some of you have done that before. You walk through and you're like, what are these little things? And you pick them off, and they're kind of hard to get off, and they stick to your shirt, and then you got to pull them off your shirt, and then you try to toss them, and the wind blows it back on your shirt. And so if you look at it in a microscope, the little hook and loop pattern inspired Velcro. So that's, I'm sure everybody has seen that or used that before. So looking at the screen here, let's dive a little bit deeper and get a more complicated example that maybe you might not have known about or seen before. So in the top left there is a lotus leaf. And if any of you have seen a lotus leaf, a lot of times they grow in wetlands or they grow in swamps, places like that. And when they grow up from the organic matter in the bottom of the water, sometimes they're coated with organic matter or muck, mud, stuff like that. And a leaf, when it unfurls, if it's covered in mud or muck, can't really absorb sunlight that well. So over the many, many millennia or millions of years or however long this took to evolve, on the bottom right, you can see a an electron microscope slide of the structures on the leaf, which if you look on the top left, I know it's a tiny picture, you can see these little beads of water, but you can't see those little nubs there. So if you zoom in, those little nubs are hydrophobic and hydrophilic and help pull and push the water into these little beads, which in the bottom left, we can pretend that lotus leaf has just come up, or maybe there was a drought, and so the leaf kind of got exposed to the muck or the mud, and it has that dirt. You can tell that kind of tan layer all over the leaf. Now, when it rains and the water comes back, or say a frog jumps in the water and splashes water on that leaf, those little beads eventually will get heavy enough, and gravity it'll start to pull that water droplet. And what is it doing there? It's creating like a path. It's like a bulldozer pushing that dirt off of the leaf. It's pretty cool. So then part of biomimicry is that innovation inspired by nature's genius. That's pretty genius self-cleaning mechanism. So you have dirt, and a plant it doesn't have hands, it can't like take a shower and scrub itself, right? So it uses the surface tension and the physics of hydrophobic, hydrophilic, and water, and the water droplet is actually cleaning the leaf off. So, and I'm not sure what company this is, but the product name is Ludosan. It's a registered product. But in the top right, there's a paint that is a self-cleaning paint. So whether that's rain or maybe dew in the mornings will collect on that paint, and it'll start to run down the paint. And you can see there's 3 streaks there that's picking up that soot or the dust particles off of that surface coating. So there's probably a multitude of buildings around here downtown that could benefit from that, especially near a giant construction zone, right? All that dust that blows around, and you have to pay somebody to come out and they power wash the building. Or the paint could just clean, it could use water to clean itself. So think about how much time and effort and money that would save. Another opportunity that's not really on this slide or associated with the slide, but I know solar panels, especially the big, maybe not so much the ones on your house, but those big fields of them, they get dusty, and that reduces their ability to absorb the light and then turn it into electricity. So potentially, you could have a solar panel with that surface that would self-clean. And then that way, again, you wouldn't have to have a service call to go out there. I know they have these fancy like robots now that you've seen. It's like a Roomba that goes across the panel and cleans it, which is pretty cool too. But if the panel itself, with rain or dew condensation, could just clean, that would be pretty neat. Okay, so if this is your first time ever hearing about biomimicry, a really good place to start is with what they call essential elements. And the essential elements, that little picture reminds me a lot of, like, if you've ever seen a cacao pod, like cacao that makes the chocolate. It kind of looks like a cacao pod. I don't know if that was intentional or not. I know biomimicry uses a lot of biological words and pictures and phrases to kind of shape the way that the human world is. So I wouldn't put it past them to have seen a seed pod and think, oh yeah, let's do that. So ethos, just a boring textbook definition here, is the fundamental character or spirit of a culture. This is really crafty. The next one is connect, reconnect. I know there's many times in my life where I've spent a lot of times outdoors. On my on my resume there, I didn't put on there, but I did hiking trail maintenance in the Adirondacks with the Student Conservation Association. And I was outside all the time. And now I have a desk job, and I'm lucky to experience the wind blowing on my face when I get out of my car and walk to my building and go in my building and sit there for 8 to 10 hours and then go back outside, and maybe the wind will blow or I'll feel some rain on me. And that's about it. That's about all the nature that I absorbed that day. So it's really neat how they put connect, reconnect, because there's so many times in our life where we're outside and then we not forget, but life happens, right? And we don't get to get outside, which, by the way, today's a very beautiful day. And future speakers, that'd be neat where the beehive thing is right there. I don't know if they could put a little shelter or something. I don't know. Stick a pin in that, future thought. Emulate is to imitate in an effort to equal or surpass. I'm sorry, I forgot to read the textbook definition for connect, reconnect. It's the cause to be associated in relationship again. So what do those really mean? To me, ethos is the why. It's the core value of your approach. I mean, so many times we recycle, or so many times we go out and we go plant a tree and stuff like that, and sometimes it feels robotic, and it's just kind of part of who we are. But it is nice to really think about, and this museum, again, is a great place to walk around and see why we don't want litter to go in a stream and then eventually get into the ocean, right? There's some very emotional things that can happen when a chunk of plastic, a turtle eats it or something like that. So that's kind of the ethos, is why, is like that's spiritual or emotional connection to the earth, to our environment. And connect is simply just going outside. I mean, again, I kind of slap myself on the wrist. Sometimes I could always go take lunch and go walk around outside. So that's a reconnect for me. And emulate is really, it's the mimic in the biomimicry. So bio is life, mimic is that to imitate in an effort to equal or surpass. But again, these three things, there's classes, multiple classes on each subject. The emulate part is the shiny part. It's that ludozan. It's the like, ooh, that's cool. That's a really neat shiny thing. But you can't really get to emulate without diving deep into ethos and reconnect. So another tool to use is biomimicry thinking. And this is a good design tool to use for projects when looking at biomimicry processes. So this tool could be just following step 1, step 2, step 3, step 4, all the way around. That certainly could be beneficial and work for a project. Or you could choose your own adventure. So if we're looking at the ring on the right of the screen there, around the outer ring, the darker green, it's scoping, discovering, creating, and emulating. And on the inside, we go from define, identify, integrate, discover, abstract, brainstorm, emulate, and measure. And at the very, very core is this very important piece of biomimicry, is that life creates conditions conducive to life. So that's a very core, it's in the DNA of biomimicry, is life creates conditions conducive to life. Yes, there are some folks who, yeah, well, what about the example of, like, I know black walnut tree, when the nuts fall down, I think there's an enzyme or there's some compound in there that is like a herbicide. So it keeps other plants from growing, which helps the black walnut tree. But that black walnut isn't falling on the ground, and then all of a sudden, for 60 miles around it is just barren, dead life. And eventually that compound will break down. Rattlesnake venom, eventually it breaks down. It doesn't just, it's not like the movie Alien where it's acid and just eats through your arm and the floor and goes down in the core of the earth. And so when I said choose your own adventure, you could be in a brainstorming session. So the very bottom of that circle, you could be in the middle of a brainstorming session and you're looking out the window and there's a bird that flies by, and all of a sudden you have this epiphany for whatever project you're working on, right? And then all of a sudden, I wonder why does that bird, okay, the mama bird's going back and it's giving the worm in there. Like, how does that happen? How does it know? It picks up the little packet of poo and then it flies away and drops the pack. Like, what's with that? And then maybe you go into define and then jump to discover, jump around. So this isn't just a step one through the end there. You can certainly bounce around. Life's principles are another great tool. And again, this is a central core. It's almost like the known rules of life on planet Earth. So there's a lot going on here. I'm not going to read every single piece here. But essentially, this is, again, there's classes that are taught on this, just on this topic right here. But on the outer ring, we have some Earth's operating conditions. So like sunlight and water and gravity. And then I'm just going to pick one of the life's principles here. So adapting to changing conditions. So that is kind of a rule, a lot of life, and another thing too is like life doesn't follow every single, like if you don't hit every single one of these, oh, that's not biomimicry. That's not what I'm saying. And that's, a lot of life doesn't, there's some life that doesn't follow every single little piece of this. But this is a tool to help you in projects and think about how to design your system or your process or your product with these life's principles, these design principles in mind. So while there's many tools in the biomimicry toolbox, I really like to play with this function bridge. This really spoke to me. Again, I think back to my geography and urban planning. Geography is thinking about ecosystems and how did that island over there, how'd the animals get from there to there, and now there are different species. That's pretty wild. And then the urban planning side is talking about curb cuts and other boring to some people, boring little, why is that curb painted red till there? Oh, there's a fire hydrant there. That kind of makes sense. So thinking about those two, the play between the natural and biology world and the human design world. I know we're all part of nature. Humans are part of nature, yes. But we design things. I mean, look in this room. Besides the wood floor here, there might be some other biological materials that have been used somewhere in here. I don't know where they're not jumping out to me just yet. But the human design world is very different from the biological world. So this bridge really is important, an important tool to think about how to pull ideas from nature into human design, or if you're in human design, to seek those ideas from nature. So some keywords to think about are function and strategy when you're on this function bridge. The function of the thing and the strategy of the thing, whether that's the human-built thing, the function and strategy of that, or the natural thing that you're trying to seek innovation from. Biomimics also frequently ask the question, how would nature do X? I'll say that again because I stumbled. How would nature do X? X meaning color, or move fluid, or shed heat, or gain heat, or breaking down those basic things that products, how does nature communicate, right? Just super simple questions. Those are important in the function bridge. So, thinking about different layers and the relationships in that bridge, we could think about it a really, it makes sense to me, it's easy for me, so I'll just present it as such. You can think of it as in scale. You can think of the micro, the meso, and the macro, right? Small, medium, big. So in the micro level, that could be like a product for the human design world. In the natural world, the micro could be biological, or you need a microscope to look at it, right? So this is a great example. Some of you may have heard this, but the bottom slide there, the bottom two slides, are a product from a company called Sharklet Technology. Sharklet Technology. So they were trying to create a coating that reduced biological entities from being on them. So they looked to nature for inspiration, and they noticed that sharks don't really get a lot of barnacles or fouling on their scales, unlike the great example of the whale out there that has barnacles, on its head, or turtles get barnacles sometimes on their shells. And even well, yeah, sharks are fast, okay, but there are some slower sharks too that don't get the biofouling either. So, okay, what's the answer there? So, looking at a microscope, the top slide there, the top two slides, that's a really zoomed in view of a shark scale, and you can see there's ridges in between the scales. And if any of you have ever been in an aquarium like that has a touch tank and they have a shark there, it's kind of like similar to a snake where you pet head to tail and it's smooth, and then you go back the other way. It feels like sandpaper, right? So imagine that feeling with those. There's the picture there with the shark scale. So they mimicked the structure. Yes, there's not plates. Yes, there's not scales. They're not overlapping, but you can tell that there's a pretty good defined diamond shape with ridges there, which that does not allow bacteria to grow as much. I'm not saying it's bacteria proof, but it reduces it. So where could that technology be beneficial? Think about all the high touch surfaces, the door plate when you walk in, or the handle when you walk in, or in a hospital. Man, how many places in a hospital do they not want bacteria to grow? Quite a few. And again, that's not saying we don't have to clean it ever, but it's using that strategy and asking, okay, I could get a cleaner that is way more effective in killing bacteria, right? But is that really how nature would do it? Maybe. There might be some salivas or some enzymes or something like that to kill bacteria in nature. But as a coatings company, they didn't want to pivot and then become a cleaner company. They're thinking about coatings. So they looked at, okay, these shark scales, let's look at the structure. Oh, wow, bacteria doesn't grow as well on that. Boom, we got a product. Also, the shipping industry. Think about how many giant ships have biofouling on their hulls, right? Those same barnacles that grow on a whale or a turtle grow on a ship. So if a ship had this as its coating on the hull, potentially you could have less biofouling and thus a more efficient ship, which means less CO2 emissions, less petroleum usage, et cetera, or a faster ship too. It could get from A to B much faster. So that was the micro. Let's think about the meso, or the middle. This really speaks to me, to the companies that I work for. In the top left picture there, you have somebody in what looks like a spacesuit there, sort of. They're shooting a gun with some fog coming out of it. Well, that's actually a process called powder coating. So they're actually, instead of liquid paint, they use powder, and the powder goes on a part, and then they bake it, which really, it reduces a lot of air pollution. But it does have its downsides. It has water usage and chemicals and things like that. But it kind of depends. Pick your poison there. What are you trying to reduce? Now, on the top right and the bottom right, most people would know that is a butterfly, going through, or a caterpillar going through metamorphosis to become a butterfly. Now, I don't know if that's a monarch or a viceroy. I'm not that great of a naturalist. So if anybody knows, you can feel free to chime in. But regardless, we'll just say it's a monarch. Metamorphosis is an extremely fascinating process. That caterpillar goes into this cocoon and liquefies itself, and then reassembles itself into this thing that flies. Like that If that doesn't blow your mind, I mean, that humans have a lot of amazing technology. You know, we have this computer. I'm talking through a microphone that's going out everywhere. But that process is absolutely mind-blowing. So you can think about this process of the human built world. We mine minerals and we make this powder and we ship it to this place, and we have this multi-stage process in the middle there that is a powder coat system. So you have water and heated chemicals, and then they have to dry, and then you spray with this powder, and then it goes through an oven that's 600 degrees or 500 degrees, and then out you get this metal part that's painted, that's orange. But the monarch butterfly doesn't go through all that. It doesn't use acids and use a 500-degree oven to make orange. Somehow in that metamorphosis project, it creates orange, which is just, again, it's mind-blowing. So at the macro or the large scale, we have a lot of really cool things here going on. So in the top left, you have a school of fish, right? And in the bottom right, someone captured a bird murmuration that looks like a bird. I mean, the murmuration is really cool. I can't believe the photographer caught that. But a bird murmuration is like a school of fish. It's similar, where the birds are all flying together, either trying to evade a predator or capture prey, or who knows? Who knows what they're doing? And then the bottom left, obviously that's the United States there, with some transportation routes. And in the top right is a piece of agar gel where they took little bits of food and put them in the major city routes, and they let a slime mold inoculate the food sources and grow between what would be the city sources, and see how efficiently they grew and where they grew. So at the system level, we could look at really big things like a Department of Transportation interstate highway system and see the way that we built it, is that as efficient as how nature would build it? Because that slime mold it doesn't know about county line boundaries and tax breaks and bridges going over a river. It's trying to get the most efficient path from food A to food B. How do I get my next meal? And it's trying to grow as efficiently as possible. There's a lot of other applications for this, like with autonomous vehicles. A school of fish, they may bump into each other. Birds may bump into each other in flight, but I haven't seen a video yet of a bird murmuration or a school of fish they freak out and they hit each other and they just all die and float around. So hypothetically, if you had all the cars on the road and they're autonomous, and somehow you pulled the algorithm from school of fish or bird murmuration, and somebody way smarter than me made some equation and slapped it into cars, and you have a truck going down the road and a bundle of lumber falls down, and all the cars just kind of use whatever that algorithm is and just kind of move around that would be an interesting application of fish schooling or bird murmurations or other migration, big system level natural phenomena. So we talked about that bridge, looking at nature and human design systems, and we have 3 different levels that we could look at it. Here's another way that we could look at it on the bridge there, is by sectors. Now, 3D printing is super fascinating. We use some of that at the place where I work now, and it is really cool, and there's actual applications that we're using it, not on a super grand scale yet, but some really fascinating, very smart ways to use 3D printing. And some of you may be a hobbyist 3D printer at home, or you use it at your work. So just kind of looking at these pictures here, the top left and the top right are kind of some typical 3D printed parts. The bottom left is pretty neat. There's a panel of UV and a liquid polymer where the UV activates that polymer and it turns solid, and then so the part actually gets pulled up out of the liquid, which is different than kind of your standard real style with a filament that 3D prints on a base and it 3D prints up. The bottom right is metal. I think it's a sintering process where it uses really high heat laser, and that's a bed of powdered metal. So it's 3D printing a metal part, which is pretty cool. And in the middle is a company that printed the body of a car, a super simple car, and they did this at a conference, and by the end of the week of the conference, they were able to drive that car out of the conference. So they printed the body, they added wheels and the motor and the drive system and all that kind of stuff. It was pretty simple. It was like to me, it kind of looked like a golf cart, but no offense to them. A lot of technology and brilliant people there. But that's still pretty cool that in a week they were able to print the body of a car and drive it around. That's neat. So let's think about how nature 3D prints. So there's probably thousands and millions of examples, but on the screen here on the left, the box, you have a feather on the top left, a yellow feather, and then you have a lobster shell on the right. And these pictures show an ever increasingly zoomed in view of a feather and then the lobster shell. So again, thinking back to the 3D printing, you're starting off with a filament or metal or some polymer, and you're adding energy to it, and you're heating it or you're printing it off there, which is, again, fascinating. But the bird feather grows out of the bird wing, and as you zoom in, there's all these different fascinating structures there, the microstructures, the nanostructures, and then you have pigments to make the yellow. So that feather comes out yellow versus the car where we have to take the metal, we either 3D print it or we stamp it, we press it, we send it through a process, then we spray it, and then we bake it at 300 or 400 degrees, and now you have a yellow car. The lobster is pretty fascinating. I'm going to start out really small in what looks like a little nerd gummy cluster there in the bottom left, right under the lobster. So those are probably molecules, and then they go into compounds. Compounds go into an element. An element goes into a fiber. You get a bunch of fibers together, and then you put them in a helicoidal pattern that increases strength, and then you put all those helicoidal patterns into a thicker edge, and now you have a lobster claw. When I was a naturalist at Kiowa, occasionally we go out in the marsh and throw a cast net out, and I was trying to catch shrimp, but I got a blue crab. And so I thought that was pretty cool. And I had a bunch of kids around me, and I went to go pick it up, and I thought I had picked it up safely. It was faster than I was, and it grabbed my finger, and I almost taught those kids some new vocabulary that day. But I kept it together, but it hurt really bad. And I know some crabs, their claws, through the structure and the musculature and the hydraulics inside there, they're strong enough to crack open oysters, right? And other mollusks. That's some incredible strength in that thin layer of that crab. Think of all the applications where we could take, again, kind of reverse engineer, to use human terminology, reverse engineer that lobster shell for material science to make whatever we want. So if I'm an engineer, thinking back to the 3D printing, I'm trying to make that material stronger or lighter or both. Am I trying to make a material that is shedding heat or retaining heat? Do I want it to absorb light or reflect light? Thinking back to these animals, again, they're 3D printing. I mean, we're kind of 3D printed, right? We start off as 2 cells. Yeah? 2 cells. And now I'm 6'4", and I'm 200 pounds. But I was 2 cells. That is really, really fascinating. And again, thinking back to the 3D printer, that's really cool that we can sinter metal and stuff like that. But I mean, just look at your own body with your eyes and your heart and your lungs and all these processes that make systems and all the micro elements that make the processes that make the systems. It's pretty wild. So I mentioned that yellow feather. Thinking about color, like what is color? What makes color? If you work in textiles, are you really trying to make a dye for the fabric that has 3% less hazardous material and has, a nickel less per gallon? Or are you just trying to make your textile blue? So how do humans make blue, and how does nature make the color blue? So within color, you have pigments, but then you also have really cool stuff like this is structural color. Many of you have seen, I don't know, I should have looked first, but I don't know if there's a section in the NRC that talks about light and prisms, right? You've seen, probably you've all seen that prism where they send a band of light through and then it spreads it out into the rainbow. Structural color uses that idea, and if you look at the beetles or the butterflies or moths there, on the top is the organism, and then it gets smaller and smaller down each row. And finally, the bottom row is an electron microscope slide, and all those little structures bend the light so that it either absorbs or reflects certain bands of light. I mean, we go back to ethos, kind of the eternal question, why? I'm not looking for an answer. Why is that blue morpho butterfly blue? It's pretty fascinating. But what's really interesting too is, so these are colorful in light, but they're not if there's no light hitting them. Is that important? Or is it not important? Are there applications in the world that we want something to be colorful when light hits it, but we don't when it's dark, or vice versa? Do we want it to be colorful at night or giving off light at night, but not during the daytime? Does nature have examples of that? Also, we get into things that we can't even see, right? That's just a visible light range. So UV and infrared, some animals can see that, and we can't. Could we put that into our built world? Not necessarily for us, but think about those autonomous cars. If the paint on the car could reflect UV that we can't see, but maybe there's a QR code in UV that we don't have to see, but the car next to us sees that and says, "Oh yeah, that's an ambulance. I need to, pay special attention or get ready to, if the lights go off, I pull over the side automatically," or I don't know. I'm just making that up, but could there be like the secret language out there that helps with other technologies? So thinking about that bridge and some of the other tools that we've looked at, and sorry, as a side note, the picture on the left, that's the only picture that I get credit for. I took that, that's my hand. So all the others I've borrowed from other sources. So that one's mine. And I was actually at a workshop in Brazil, and that is a tortoise beetle, which when I was a naturalist in South Carolina, one of my favorite critters was the palmetto tortoise beetle, which looks like a little, those little candy dots, which is a complete waste of money. Sorry, company that makes those. But those little dots, you get like in the summertime at the pool, the little snack shop sells the little sugar dots on a piece of paper. This is like it's a little like half sphere, and this is a type of tortoise beetle. So if you're a biologist, thinking about jumping this bridge, right? You've got the human design on the right with the Volkswagen beetles, and then you have a real beetle, a biological beetle on the left, and those are its larvae, the little black clump there. Its little larvae. They protect themselves with, is it frass? Like beetle larvae? The poo is called frass, I think. So they protect themselves by waving the shield of poo. Like, one, it's funny, but two, that's pretty wild. Like, who taught them that? How did they learn that? Or was that part of their DNA? They just like make your poop shield and hang on to the stick, and mom or dad's gonna watch out over you. So if you're a biologist, you're thinking about this tortoise beetle, and you're saying, what does it eat? Where does it live? Why do the babies have this little poop shield? How does it communicate? Did it teach the baby? Like, there's so many questions about that. Thinking about the structure of the shell, What's the polymer made of? How's it oriented? If you look, you can kind of see the outer edge is clear. You can kind of see part of my fingernail underneath the edge of the shell. So it's clear, it's white, it's orange, and it's black. And that's just kind of the surface of the questioning that somebody could study this little tortoise beetle. Now, if you're a Volkswagen engineer, what questions are you asking? How can I make my product stronger, faster, lighter? Can it use less resources? Can we get a better ROI on this unit? Into the future here, can the cars communicate to each other? I don't think the older Beetle can communicate to the newer Beetle, but maybe the newer ones can communicate to the other ones. What if the biologist was in the room with the engineer? What if the engineers took a field trip to Brazil with the biologist and they stumbled across this beetle and then they had a whole workshop on it? So that's where that bridge is really important to think about. Again, the function and just bringing it into basic questions. So if I was a Volkswagen engineer, I would want to know, could I make the whole car out of one polymer? Can the tortoise beetle do that? Is its outer shell just one polymer, or are there multiple polymers? Because there's a clear section, and then there's a colorful section. You look at the Volkswagen Beetle, there's a clear section, i.e. the windshield. Imagine if you could 3D print that beetle. We already saw an example of a 3D printer in a car or at a conference print off the shell of a car. It's not roadworthy, it's not NISTA or whatever the acronym is, tested, certified for road application, but I think that came from 2 years ago. So this is the bridge that I was talking about. So yes, there's a lot of like the ethos and the reconnect. You have to learn that. You have to learn the biology design tool, design method. You have to learn the life's principles. There's a lot of stuff you have to learn to be able to put that bridge into application. But I wanted to introduce biomimicry with the bridge in mind, because that's really important to me, and that I think a lot of us, especially here at the NRC and those in DEQ, we come, or I'm saying we because I used to work for DEQ, we come to the department with a passion, with that ethos already. I mean, it's kind of mostly a no-brainer of why people go work for DEQ with that ethos already. So then how do you take what you learn, especially if you're a biologist, how do you take what you learn and get it out to the world for those engineers to collaborate with you? So what can you do? You can certainly learn more. There's some resources in 2 slides. You can network or be open to collaboration, right? You don't necessarily have to seek someone to collaborate with, but you can be open to collaboration. You can put your work out there if you're a biologist, if you're an engineer working for a company. And I think a lot about engineering and manufacturing, but a lot of these, there's a social aspect to this too. A lot of animals are social creatures. So if you're working for a nonprofit, if you're working for HR, there's probably applications from nature that you can pull in. How do you get people to follow all your rules and regs and other little treats you can give them? Well, guess what? Did your mom or dad ever give you a treat when you did something good? Okay. So nature, there's probably social applications that you can pull in. Architectural, there's definitely design applications. There's pretty much any industry out there has some draw somewhere in nature. So network or be open to collaboration. And then finally, go explore. Outside preferably, but obviously if you're in a really cool museum like the NRC here, or the Natural Science Museum or an aquarium or wherever, you can still see, there's live critters here. I'm looking at them right now. There's some fish over there. There's some really cool scientists who work here too. So you could do all 3 of these right here in this museum. You can learn more, you can network, there's people to talk to, and you're in a really cool spot to learn about nature. So I recently rewatched Ferris Bueller's Day Off, and so I was inspired to put up a slide. If anyone has any questions or comments?
Let's give Scott a round of applause.
Thank you so much.
Great stuff. Thanks, Scott, for being with us today. Thanks for sharing.
My pleasure.
If you're here in the room with us and you've got questions that you want to know more about, wave at me. I'll bring you a microphone that lets everybody in the room hear and those watching online. If you're up on the balconies, just wave down at us, and then we'll call on you and you can yell at us, and we'll use the microphones to repeat your questions. And if you're watching online, I see some questions are already coming in on the chat. Type those up, get those submitted. We've got people standing by in order to make sure that your questions and comments make it into the program as well. And Scott, one of the first questions that came in said, Renee wanted to know, or said that you've found and talked about lots of really interesting and cool and amazing examples of biomimicry. What do you feel like is something that's truly amazing that people are using in their daily lives, but might not recognize as being nature-based design?
Ooh, that is a good question. Thank you, Renee. I did talk about Velcro. I think not to reuse that example, but I think Velcro is something that's been around a really long time, and it's something that we all probably have some article of clothing, or if you play sports, you have some sporting equipment or fishing equipment, or something in your life probably has Velcro in it. And the connection to that is thinking about a seed pod, a burr that has the little hook design on the seed pod to grab on to probably the fur of an animal that's walking by. So the seed pod hitches a free ride, and the animal is knowingly or unknowingly moving that seed pod somewhere else, and then it falls off, and now that plant gets to distribute itself around a bigger area versus just falling straight down or being wind blown or wind pollinated. So Velcro would be the answer.
Hook and loop closures got us to space, I think, so
Yes.
That's great. What are some mistakes designers make when trying to apply biomimicry solutions?
Ooh, that is a good one. We definitely talked about this in class, and I again, there's so much here. There's a whole master's program, right? So this is whittled down into an hour discussion in a whole book. But I think sometimes, just like with green or environmental, there are good intentions that potentially that idea is mal-applied or applied wrongly, right? And so sometimes bioutilization, like this wood floor, right? I mean, this is a great floor, don't get me wrong. It's held me this whole time without me falling through. But there's a difference between bioutilization, cutting down a tree and using it for lumber or making paper, or just using the thing for direct thing's sake, going out and eating an organism, right? That's bioutilization. And then there's also, similar to greenwashing, if you've heard that term before, if you paint a car with zebra stripes, that's not necessarily biomimicry, right? So studying the zebra, why does it have those stripes? Is there anything with the hair, the skin, really having a deeper appreciation for that, and thinking it back to some of those tools about understanding the zebra and then applying it to the car. There's definitely applications for that, but just painting it zebra pattern, that's not biomimicry.
I did see a study where they painted cows to look like zebras. Does that count?
I don't believe so, but I'll have to check into it.
We can chat about that one after the
I wonder
show.
what the milk would taste like.
Like I don't know. All right, next question.
There was the shark skin suits that they used for the swimming Olympians that worked so well they had to ban it.
Yes, I heard about that. Yes, yeah. So that I believe some of that was a similar adaptation to that, like the sharklet technology, or studying the shark scales and applying it to the suit. Yes, yeah. So that is utilizing biomimicry, and I go back to that life's principles. That suit probably doesn't have all the life's principles in it, right? It's still probably made out of a petroleum-based textile or something like that. I'm not knocking the suit and saying it's bad. It's just that might be just a small application to that. But yes, great example.
What are the oh dang, this is weird. Can you what other places have you been to study like other animals, and what are your favorite three?
Oh man, favorite 3 animals? Okay, so first part is what other places have I been to study animals? Well, I talked about when I was a naturalist at Kiowa, so in Charleston, South Carolina area, the marsh, very similar to the marshes we have here in North Carolina, right? It's kind of similar habitat. One day I saw a pistol shrimp. So if you don't know what that is, go check it out. So a pistol shrimp is really neat. Its shell is very like rainbow, translucent. It's really cool, and they're very elusive. So if you're in the marsh, you see these little holes in the pluff mud. Some critter made that, and there are pistol shrimp that live in there, and they shoot their arm out super fast. And there's they use hydraulics to do that, right? All of our animals that have exoskeletons, their body is goo in the middle, and so a lot of times they use hydraulics to move around, unlike us that have muscles and bone. Yes, so it might be a pistol shrimp, it might be some other type of shrimp that eats. One of them eats fish, so it has like a spear that shoots out and like stabs the fish and then brings it in. Nom nom nom. And then there's another shrimp that has like a giant ball that smashes mollusks, and I've heard that hits so hard it cavitates, and it creates light. Like it hits so hard that it creates light because of cavitation underwater. Yeah, so that again, mind blowing stuff. So Charleston was fantastic. The biomimicry workshop that I did in Brazil and Rio de Janeiro. There's a beetle, a click beetle. We have click beetles here in North Carolina, but the click beetle actually was bioluminescent, and it had 2 little spots on its back that when it was agitated, it would light up these 2 little eye spots. So that blows my mind. I'm honestly, that's probably a bad question to ask me because I'm fascinated by a lot of things and everything. But so we have pistol shrimp, we have the click beetle, and I don't have a third. There's just everything. I did mention the tortoise beetle. I like the tortoise beetle. One fact I heard that since it's a hemisphere, a half sphere, part of its defense is that it when it's just kind of walking around doing whatever, and if it feels a predator, it'll pull itself into the leaf, and then you can't really, like, imagine a soup bowl or a cereal bowl. Have you ever, you're washing dishes and you flip one over and then you're like trying to get your hands under the bowl. It's hard, right? So that tortoise beetle like pulls itself in, and it's super strong. I mean, a human, we can pick it off because we're a giant, but if you're a bird or another bug, it's slippery, so it can't grab, and then it's pulling really hard so that it can't. The predator is like, forget it. I'm just gonna go eat this thing over here. So mostly insects, I think, is the moral of the story. Yeah.
Fantastic stuff. One last look around the room. Otherwise, that's our time. Scott, thank you so much for being with us again. Appreciate you sharing your knowledge and insights, and it's fun to see what you're learning so much about and the ways you're looking to apply it into your life and the things you're interested in, and then we get to experience that, learn, and apply it as well. So thanks for being with us, and thanks for sharing today.
My pleasure.
And everybody, yeah, go ahead, one round of applause for Scott, yay! With next week's holiday, Thanksgiving, we won't be doing the Lunchtime Discovery Series next week, but we will be back here again on Wednesday, December 3rd. That presentation will be virtual. We'll be on the museum's YouTube channel and not here inside the theater, but we'll be talking with Karen G. Lloyd from the University of Southern California, who's going to be talking about her book, Intraterrestrials. We'll be discovering some of Earth's extreme wildlife. Don't miss out on that program. Head to the website, eenorthcarolina.org. That's the website for the North Carolina Office of Environmental Education, where you can see future programs and events, including the Lunchtime Discovery Series, and sign up for the email newsletter to get the link in your inbox when we're ready to go live. That way you can come and join us. And you'll also know which programs are going to be here in person, so you can come grab a seat in the theater and meet the guest speakers, or just tuning in online. So thanks for tuning in, everybody. Thanks for joining us. Have a great rest of your week. Happy Thanksgiving, since I won't see you next week, but I hope I'll see you again soon. Bye, everybody.